Okay, so what do we have? Now I'm talking. Alright, so for today, I was thinking of doing some integrated logic circuits study because of our quiz tomorrow. I will bring that up right now. Oh. Alright. So, we can, if we look at comment associated with my grades. Oh, great. Whatever. That's fine. If we look at announcements, pop quiz tomorrow, it states, please review the class notes from last week. There will be a quick pop quiz in class tomorrow. So it's TTL families, fan out, VOH, IOH, IOL, timing, and truth tables of NAND or not gates. Alright. So, going back to our notes, just curious on yeah, it looks a lot better on the DSLR. So for now I'll stick to the DSLR. I will, in fact, give me a second. I'm going to try something a little different today. I'm gonna use a memory card and record. Just curious on what exactly happens. Okay, so recording doesn't seem to work or do anything, fortunately, but I guess I'll leave the DSLR like this. If it does shut down, it's because it's overheating, but that's just the camera itself, which is stupid, but whatever, is beyond the point. Let me just get a few things ready. Just gotta check one thing. Okay. Alright. Let's get to it. So, we begin, like it states in pop quiz tomorrow, TTL families, fan out, VO, IOH, LOH, IOL, timing diagrams, blah, blah, blah. So, let's begin by going through a few things. What I have written down: digital IC. Traditional IC is called the DIP, dual inline package, blah, blah, blah. It's a lot of other things. And we have different family names, acronyms, blah, 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 which is down here, but that's beyond the point. So, first, TTL families fan out. So, fan out, as stated here, is a logic circuits drive. Basically, logic circuits drive other logic inputs. Sometimes same family ICs drive each other, but most of the time it is mixed. Whatever. The term fan out is the maximum an IC can drive other gates. So, if we continue, we get to finding problems with fan out. This is the problem for fan out. So, how many NAND gates inputs can be driven by NAND gate outputs? So we begin by finding the IOL max, or the the low output current, as well as a low input current. So on the datasheet of an AND gate, it says low output current at 8 milliamps and low input current at minus 0.1 milliamps because it's going in the opposite direction. So, we begin in this current state where this NAND gate is being pulled low. So, we see that the 5 volts from the second gate here going through a resistor, which is over here. Just write that. Sure, this is R, this is R. And going through the resistor to the output, through the output of the first gate and straight to ground. So if we take the low output current, this 8 milliamps, and then we find how many times can we fit this into this. Basically, we take this and we divide it by this. Hopefully I'm doing this right, but eight, 10 to the negative 3 divided by 0. Oh god. 1 times 10 negative 3. 80. So, with this calculation, we see that in this configuration, we can have 80 of these gates pull this one to low. But we can't only leave it there because we need to check at the high, in the high state per se. So, input high output current and high input current. So in the data sheet we see this as negative 0.4 milliamps and 20 microamps. So if we go to the next page and we see here the same diagram with a resistor here and a resistor here. If the inputs are pulled low, therefore it goes high through this one, and in this case it's going to a low. So we take our 0.4 milliamps, which is when we remember which is our high output current, and then we divide it by our high input current. Now, is it the same here? We divide this by this, low output current by low input current. So 0.4 times 10 to the negative 3 divided by 20 times 10 to negative 6. We get 20. Therefore, the problem is solved, and it states that the maximum number of devices we can use is 20 when driving in this configuration. Therefore, we have to use only 20. We're not allowed 80 because it will fail after that, give or take. Of course, there's all over the tolerance, blah, blah, blah. But that's fine. As you can see, I'm just switching to the camera so I can basically just look over what else I have. Invalid voltage. We got CMOS. It talks about but he's not wanting us to he doesn't want us to study that right away, so let's go back. So again, what does he want us to learn? VOH, IOH, timing diagrams. Timing diagrams. So let's go ahead and look for the notes that he gave us. I do not have my NAS open, so I can't find it, meaning I have to go through Omnibox. Where does he talk about timing diagrams? Let's look for that. Guess propagation delay. Logical signal always experiences a delay going through a circuit. The two propagation delay times are defined as time propagation high, low to high propagation delay, and high to low. Delay time in going from logical 0 to 1. So 0 to 1 at this 50% mark. So in terms of propagation delay, is when it becomes a logical high, and then again at a 50% mark, and the same for the other. So if we were to take this into account, paper. So, we have determined that of the things to study, we begin with propagation delay. We can say for propagation delay that at 50%, either low or high, either low or high, a state will go from low to high H to L at 50% of the rise time. Which, I mean, and again, this propagation delay is created by the IC itself. So if we were to go back and look here, we see that the 74 series, the propagation delay is 22 nanoseconds, while something like the 4000 series is 2500 nanoseconds. So, this tells us that we need to take propagation delay in consideration at all times, and we need to, of course, add it together. I mean, especially from our notes last semester that we learned about the basically how we can add propagation delay and how it's multiplied in terms of flip-flops. But in this case, we won't really need to consider that, because it seems that in this course we're learning, I guess if I had to guess, it's pretty much the basics of logic ICs and how they work at the start, but then we'll get to other stuff like the basis. But I mean, let's not get ahead of ourselves now. We still have lots to do. So again, TTL families fan out. How they work, like we saw what I had written down in that one example, how to find depending on the case. So what we begin by doing when it comes to fan out is TTL fan out first. We get info on on gate from datasheet. So in this case example, we want to get IOL, IIL, IOH, and IIH. Then in this example in particular, you find the maximum a gate can take a input from another gate, or how much it can output. So we saw in this case that the high output current, so if it's a logical high at the output, the amount of current that is outputted, in this case 0.4 milliamps, has to be considered, because for the second gate here, we're looking for high input current. So if there's a logical high going into an input, how much current will be produced per se. Produced. Because it's produced here. Obviously, it's not, I guess it's how much it's produced, and this is the total. Yes, so the total it could output is the high output current, and the total that is being drawn, which is the high input current. So with this, in this particular case, we need to find how much one gate can drive this many gates if it's if the output is going to gates that draw 20 microamps per gate. While in this particular case, we need to find the total amount of current that the first gate can take, as the second gate draws current backwards. In other words, this gate can take a total of 8 milliamps at its output, but in this particular example, it's drawing 0.1 milliamps from the second gate. So we then write find total current and output can give out to other inputs, other gate inputs, and find total current being drawn back into a gate output. So in that case, I mean, again, that's just this is terminology, but I mean, in that case, it's for current, as we have written here. But there's also voltage. That voltage, I mean, in that case, will basically, based off the data sheet and what it tells you, how much is being, I guess, it's dropping back or dropping forward. Hello, Ivan. Just doing some, just explaining my notes to myself and onto the video. See if anybody's, if this is ever useful in the future. So, family fan out, which is basically what we just did, with the example here. Then we have VOH, IOH, IOL. I mean, we can look at that on the PowerPoint. If he mentions that again. I guess basically explaining the different minimum maximums at each one. I mean, that's based off, if you look at this in particular case, let's say invalid voltage, when it's a logical high or when it's a logical low, so ranging from 2 to 5 volts, in this case of a TTL. So TTL, this anything zone, this gray zone, intermediary zone, this intermitting zone, which is between 0.8 volts and 0.8 and 2 volts, which is invalid. Where a logical 0 is 0.8 to 0.4. So what we can see from voltage minimum and max says in the definition, so let's say high input voltage, minimum voltage level required for logical 1 at an input. So I mean, that's within the notes already, but this is basically what it is. Camera is hot. So, all right, wait 1 sec. All right, Evan, I'm going to be right back. I'm going to just do something quickly. So, yeah. Give me 1 second. All right. All right, I'll be back. 1 sec. Timing diagrams, truth tables of NAND and or NOT gates. Truth tables of NAND or NOT. Okay, I guess. Hello, Evan. Actually, let me see if I could get the can I crop this? Can I crop this? That is the question. No, I would like to crop. Switch back to here and search that up. Crop. Window capture. Right click and source filters. Oh. Filters? Yes. Filters. Where's filter? Right click on source, filter, crop. What the fuck? Easy crop. Is that visible on stream? Not really. If it's expanded all the way, yes. Oh. Let's try this. Oh, that makes it harder to read. How the fuck? No, but yeah, I guess. Right. Whatever. Okay. Well, what do we have next? NAND or NOT gates. Okay. Well, truth tables for that. Yeah, I guess. If I do it on Twitch. So, I guess we can do truth tables. If that's really necessary. So, truth tables for NAND or and just do them all. Nor not XOR X NOR. Okay. So NAND, which is this little fella. If we look at the truth table, AB, do wait, one more X. Nice truth table. Hope you agree. Let's just continue. Let's do AND, which is this. AB. The dog is barking for no reason. Too many states. Too many states. So let's start drawing our states. So 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1. Fuck. 0, 1, 0, 1, 0, 0, 1, 1. 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1. So for a NAND gate, it is always high. It is only low if both are high. 1, 1, 1, 0. AND gate, it is only high when both are high. A NOR gate, it is only high when both are low. And an OR gate, it is only low if both are low. So the opposite, or mirrored. Mirrored. Did I just do that wrong? No, that's an end. That's an end. Never mind. I did it wrong. I did it fine. I did it fine. See if my camera is too hot. Let's quickly do XOR. Just some of this. And XNOR. Which is some of this. I'm gonna choose table for this is 0, 1, 0, 1, 0, 1, 0, 1. This is exclusively OR, so 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, which is not exclusively OR, so everything else. So exclusively the same. All right. So I just have to basically keep this in mind, remember these terms. So same for V, OL, VIL, and OH, and VIH. If you remember all this, what each one means. So low output current is the maximum amount of current that will produce a low at the output. Is that correct? Current that flows for an output at logical zero under specific load conditions. Oh, there is no max per se, but I guess voltage gets the max. So, but if we were to look, I mean, if we looked at, let's say, voltage input, low input voltage, let's go to this, low input voltage, it's the maximum voltage that will go into an input and will be read as a logical low. In this case, for TTL, we've already discussed that it's either from 0.8 to 0.4. So 0.8 would be the max. 0.4, I mean, 0.4 to 0 would be the lowest. So within this range. And for low output voltage, as what did you just say? What did we talk about? Input voltage. I mean, low level input voltage, right? What about high level input voltage? Well, in that case, it'd be the minimum, because if we take a look, here, the minimum for it to be a logical high for TTL is 2 volts. Anything below that will go into the invalid state. So anything from 2 to 5, TTL, they run on 5. It's a CMOS, of course, it varies. Of course, look at the characteristics of it. It can go from 3 to 15 volts. As opposed to 74 series can output 2 to 6. So, it's basically the idea. Okay, so I mean, none of this is very complicating per se. So, I mean, do I have to memorize all of these propagation delays? I mean, that doesn't seem logical at all. Whatever. I'm gonna do whatever. At this point, I'm gonna organize all my stuff. I'm gonna also go turn on my NAS so I can get some files in order. I will be right back. But before I go, let me play some music from freemusic.com. Let's go on their videos and click this one, and then alright, I'll be right back.
summertime when you saw me like a movie scene. We were crazy like a teenage crime. You picked me up and it had 69. Every night we snuck out. So I've been waiting by your house. Every night we snuck out till our sun will rise for the last time. Stay by your side. For you I stay by your side. Would you stay by my side? For you I stay by your side.
Okay. So, I'm tired, but I'm going to do whatever. So, yeah. Might as well. Get my stuff in order. Something else I could do on stream? I guess I could, diagnose one of my problems, or I guess we'll just chill. I don't know. I'll see. So, yeah, my audio amp. Yeah, I could. I mean, at this particular moment, as you can see, like this, it has a lot of problems because it's not making good contact when I put voltage across it. So when I supply voltage. So what I'm going to do is from here, I'm going to move it onto another breadboard. I don't know what, but I don't know why I'm having issues with this. Because, I mean, previously I didn't have, but now I do. So I'm going to try to move it. I'm also going to try to reduce the size of these I have one of these inductors, but I'm going to try to reduce the size of these other ones. But in the meantime, I'm going to get some of my things in order. By beginning, getting my this folder to my server. It hasn't opened yet, so I gotta wait. Well, I gotta wait. So I guess we can go right away on the audio amp. Let's see. What can we do? This song. I hope it's not too loud. I don't think so. Okay. Okay. Yeah, I guess I should. One sec. Let's do some trippy stuff. While I listen to the stream, I'm gonna replay it back, and it's gonna be an endless loop. Of me putting my phone on the table. Yeah, I think it sounds okay like this. Switch to the cheaper camera. Cheaper, I mean it's $100, but whatever. So I need to replace these capacitors with smaller ones, so it'll be easier to put it on a perf board like this. So I mean, I could take out the chip, the all this stuff, and actually see on the perf board itself. One thing in particular is, can this fit inside? Indeed it can. Well, wrong side. Right. Already one capacitor takes up a lot of room. I mean, these are 1000 microfarad capacitor rated for 50 volts. I mean, from Abra, of course, I have a capacitor kit. Can't even see that. Exposure is so off. So on this board, I will need if we look, this is 0.1K. So for the capacitor kit was $20, I think. So even the price on this, no, but it was $20. But I mean, here it comes with all of these, and on the inside, comes in bags and all prepared and everything. So this one that I saw had 0.1K. So 0.1 picofarad times 1,000. So that is 1 nano. No. 0.1K picofarad. No need to guess or be dumb. I has multimeter for that exact reason. We'll set it to capacitance and we'll put our leads across. 100 nanofarad. And these are 224, so 224, 22, 220 nanofarad. So we need 100 nanofarad and 22 and 220 nanofarad. On this, there is microfarad, pico, and microfarad again. So there's no nanofarad in this kit. Only microfarad. So that we're shit out of luck. It's fine though. We will proceed anyway. Let's turn that off. Okay. So if we look at the data sheet, or rather on YouTube for de-amplifier, obviously I'm going this one and we pause. There it is. There's the video. Tells me the answer to everything. At the bottom is just a copy of the top, so you don't have to worry about that. In any case, let's try to reassemble using this schematic. Let's add display capture. Let's go to filters and do default. What the fuck? Let's remove that. Let's add display capture again. Okay, so from the video, it says that we need to set it in this configuration. So I'm going to go about to do that, but I'm going to try to put it on the perf board. So let's try that. Let's remove the audio input. Remove power, left and right, and we will take this capacitor, try to put it as far away let's try to maximize our distance by sticking everything together like so, and trying to assemble it on the breadboard. Let's turn this off for now. I mean, come to think of it, these are pretty big caps, but the kit does have 1000 microfarad capacitors, so we could use, if I find them, that is, 220. They're the biggest ones of the bunch. 470. There they are. 1000 microfarad. These are rated for 50 volts as well, but they're by a different manufacturer, so they are considerably smaller in size, which will be beneficial in this case. Quite beneficial, in fact. I mean, we can separate it a little more. Already, it's a lot better. So we'll try using these. We need these. We need this. We need a 10 microfarad electrolytic. We need some 1 microfarads for inputs. We need these ceramic 0.68 micro. We need these nice power inductors at minus 33 microhenry. Some more capacitors. All these jumper wires must go. And we're left with our IC. So let's take it out. Jumpers I'll deal with after. And we'll use this breadboard. See if this is better off than the other one, and we'll reduce the size. So we begin placing this. Do we need that much distance at the output? Well, looking at we can see that at the beginning we need a connection to 5 volts, a connection to ground, and 2 for audio. So this entire side can be connected directly to one of the buses here. Try the camera. So on this side of the IC, it could be connected directly to one of the buses. So we will look at the also on the schematic, or basically the other side of the IC, will be connected in a weird order per se, especially if we look at AVC 1 and 2, where there's a 0.1 microfarad as well as a 100 nanofarad and a 10 microfarad that's in parallel with ground and 12 volts when for those two pins, as well as the gain pins have to be connected to to 12 volts. By the way, this YouTube channel, Afrotech Mods, very interesting stuff. Alright, so let's go back to the camera. Ooh. And let's try to assemble it. So we begin with we need to put a 0.1 microfarad, just this from the ground to 12 volts. So we need to connect this to ground over here, and then we're going to take a jumper wire from that same pin and put it to 12 volts right behind. And we're also going to do the same thing for the other side. Down here. And we're going to take another red jumper. And we'll put it in here like that. Okay, so we put it like this. So let's put the desktop so we can see. Oh. From here, so let's bend the pins a little bit. The pin right after is SD. SD, if we look at the data sheet of this IC, which I have on my desktop, SD stands for shutdown signal for IC, low disable, high operational, TTL logic levels with compliance to AVCC. So this, because it's active low, we want it to be operational. Therefore, we will take a jumper wire like this and place it high. In that case, I'll use the one on the other breadboard I have here. Connect that pin, which I could use a shorter one actually. That pin to 12 volts. I will get myself some tweezers. It will only be easier. Tweezers. So we'll place it like this, put it high, and then ground. Well, we will just ground the next pin for mute. Mute if high will mute the device. Then after that, we have left in and right in, so it's these two pins right after. What I'm going to do is use two different wires. I'm going to use red and white to indicate right and left. So it begins with left, so we're going to take furthest pin to the bottom for each, and these we're just going to put the right here. Because we need 1 microfarad capacitors that will connect to the input of our input, as you see here. So we have our 2 wires, and we're going to continue next. After that, let's remove left and right first, so we can put in the other wires and the other components. After that, we need to connect to the bypass pin, which is the 6th pin on the chip. We need to add a 1 microfarad capacitor and connect the negative lead to ground. So we have mute set to, oh, I set that to high. Set to ground. Then take this left, right, pin right after. We'll use the furthest. And then we need another 1 microfarad capacitor. Oh my god, cat, seriously. Hello, cat, how are you? Connected to ground. Very good. Very good. I'm just working on my app again. I'm trying to reduce the size because I had put it on this, but it wasn't working well, so I'm going to bring it onto this breadboard instead. So what do we do now? V-clamp. So right next to this one, we also need to do the same thing and put a 1 microfarad capacitor. Capacitor. So from the end to here. Then the 2 other pins next to the capacitors, those need to be grounded. So A ground 1 and A ground 2. So I will take some green wires here. I need to change one thing about the video. Oops. here. I need to just change an exposure. Make it a little more yellow. It's hard to see, but I'm going to zoom in with my DSLR after, so you'll be able to clearly tell what I'm trying to do. Let's remove these for now. Move this pin over here. And I will then ground pin this pin and the pin right next to that. So we have, and then we will get our right in and our left in. So, take a look at it in the DSLR. We have each voltage in with capacitors that are set to ground and a jumper going to VCC. Then after that we have our shutdown signal set to high. Then we have our mute set to low. Next to those is the left and right, which are connected to two capacitors. Then after that, we have a capacitor here set to ground, two other pins set to ground, and another pin set to ground. So what we're going to do now is start to work on the other side. So the other side in this case is a little different. It requires two ground connections. So ground at one corner. And ground at another corner. Are you intrigued, Cat? Or did you already give up in my stream? Okay, so next on the list we have to deal with gain pins. Gain pins are easy enough. So all we have to do is look for pins number 14 and 15. So this is ground. This is right out. This is bootstrap. Gain 1 and 2. So we're going to set this high, as well as this high. Like this. Liar, Cat is a liar. Liars. Then we need a 10 microfarad capacitor and another 100 nanofarad capacitor. So this is the same deal. We connect one pin to ground and another to VCC. So I will do that. Next to both gain pins, I'll put the one. Oops. Like so. We'll put this to high, and then we will take a cat. And the pin directly next to this other capacitor, we need to put a 10 electrolytic, where the negative lead goes towards ground. And then we connect that same pin to the 5-volt rail, or rather 12-volt rail. Okay. Now we have our outputs. So I was able to reduce it to basically this. Can I do it more? Probably. By making just jumpers and eliminating these wires, but I can't really reduce the size anymore to this. So I'm just going to go and take the output pins, like so. We'll do 2 blue for right side, and then we'll take 2 green for left side. Actually, I have 2 reds, so I might as well use reds. And 2 greens for left. Left, white, which is not red, so ground, blah, blah, blah. You get the idea. Checking if it's set up properly. It is. So that's my left audio, and this is my right. Next, we need these capacitors, these 0.22 microfarad capacitors, and I need to connect a bootstrap, which is the second to last, which is the third to last and third to first on each side of the IC. So this one has to be connected in parallel with each side. So tell me about your day, Kat. What did you do today? From there, we need... I'm going to put another wire right here. I'm going to actually, come to think of it, these actually might be too close to each other, so I'm going to move the inductors away. From each other. Yeah, I know, but I've already had bigger jumpers and it was fine previously, so again, I'm making it smaller than before and on a different breadboard. So I'm going to separate the two inductors because last time they were very close to each other. They were actually like one was here, one was here. So it would make sense that they could interfere with their own magnetic fields. But we'll see from here how if it works any better. So from here directly, we need to place this inductor in parallel with two caps. In series with two caps which are in parallel, whatever. So let's take the 0.68 microfarad capacitor. Which connects directly to ground. As well as this, which connects directly to ground. These leads are garbage on this fucking capacitor. Capacitor. And then we take our 1,000 microfarad. Like so. So it's definitely reduced in size. Again, I could reduce it even more. But this distance, I need to make sure. So, let's try it. We now need a input signal. So I got from this really janky thing at Addison. I need to get some. I need to get some tiny speakers. I'll be right back. I'm I guess I could try that. If it actually does something. So I have these tiny like 4 ohm speakers that I got from like Budweiser speaker Bluetooth thing. So I'll just use that. Okay. So we need take 12 volts in. Yeah, I guess, but I do actually have heatsink. Just plop it right there. Take this for the negative. Place it here. And jump to the other side. I mean, it was working before per se. It could have been because they're too close, but I mean, right now it doesn't really bother me. Totally honest. Wrong ground. Correct ground. Positive going into the positive rail. Negative, negative, blah, blah, blah. Okay. Okay, so let's look again. So we have our input, right and left channel, and ground, of course, going into 2 capacitors with the negative going towards the input. The right channel, left channel going into the IC on pin 4 and 5. Pin 3 must be connected to ground. Pin 2 must be connected to 12 volts. This over here, this capacitor, has to be connected to ground as well as jumped to 12 volts, which is what I've put 12 volt input here and ground there, of course. On the other side, or I mean, if we continue, we have 1 microfarad capacitors here and here connected to ground, as well as the 2 other pins connected to ground, and the same thing for this capacitor. On the other side of the chip, we have out of focus. There. We have our ground pin here and here. Then after that, we have the output pins with the green. This is the left audio and the right audio here. Inside we have the gain pin set to high for both. And then we have another capacitor here and here are set to ground. This being a 10 microfarad capacitor, and this is another 100 nanofarad capacitor, and then also shorted to ground. From there we have the output of a bootstrap, which is third to last, and as well as third from the first, third from the last, connected in series with a capacitor. And from there in parallel from the pin and the output, which you can see here and over here, which is down at the bottom in that case. So then we have that connected to an inductor, which is connected here, and then the same thing at the other side, which is connected here. From there, it's connected to, in parallel with two capacitors, a 1000 microfarad capacitor, electrolytic, as well as a ceramic 0.68 microfarad capacitor, which is going to ground for both. And this is the outputs, left and right channel. So let's try it out. I think it won't work, but we never know. So here, left and right. So we'll designate a speaker to each. And we also need a ground connection between both, which can be used with alligators. I'll be back. My amazing variety of alligators, none of which actually work very well, but that's fine. So we have our positive connecting to our right. Then our left audio, we will use white to connect to the positive on the left side. That's just exposed, I don't give a shit. And then ground between both. But we need another alligator. And the final connection to ground. Right here. From this jumper. So let's try it. With nice banana clips here and here. Let's play some Initial D, Deja Vu. Let's do that. So that's the sound of the iPod itself. Let's connect this. And let's put voltage through it. And see what it does. Oh, over here. Through the inputs on this Keystone 3.5mm audio jack. So on the back of it, there is these like little tabs. Okay. Bench press 12 and go. Well, nothing exploded, so let's try it. Nothing's happening. Okay. Great. All the capacitors fell on the ground. So the question is, am I getting 12 volts? I indeed am. So what could be the issue? Is this playing a sound? So let's play something and let's reduce this to millivolts and measure at the ground the input overload. Let's put it to higher voltage. Measuring 11 volts into the IC. Why the fuck am I getting 11 volts? Excuse me? Okay, let's not use this. Okay, well, try it now, I guess. It's not drawing any current, so something is missing from here. Something is definitely missing. Let's see. Ow. Can't I? Oh. Guess not. Thought I could be clever. I'll be a little less clever, but what could it be? What could it be? $12 volts measured. $12 volts at each input. 11 volts measured at ground. 11 volts measured at ground. Okay. Let's check. Ground connected to ground. Ground 5 volts to 5 volts. I don't know why it's doing this. Once again, it's not 11.11 volts at ground. Okay. Let's try this. Well, I'm gonna investigate this further another time. Alright, so anyway, I'm gonna get going. See you, Evan. Goodbye, cat. See you at school. Goodbye.